The Polaris Variable Transmission, or PVT, was developed by Polaris engineers in the early 60s for use on snowmobiles. And in 1985, Polaris revolutionized the industry by introducing the first ATV with our completely automatic transmission. Over the years, Polaris has continually improved on those designs, and today, PVT is undeniably the best in the industry. This lightweight and highly efficient system has many advantages over manually shifted transmissions. There's no need for the operator to select the proper ratio for the terrain or conditions. PVT does it automatically, ensuring maximum performance without the complexity of automotive-style transmissions. In the next few minutes, we'll show you how the PVT system functions, how to perform basic adjustments to keep the system running at peak performance, and how to disassemble, inspect, and reassemble all system components. In addition, we'll show you some basic setup situations to help you quickly diagnose PVT-related problems. The PVT system consists of two separate clutch assemblies, coupled together by a specially designed belt. Both clutches are basically V-shaped pulleys with one stationary and one movable sheave. The primary, or drive clutch, is RPM sensitive and acts as the engine's main RPM controlling device. The secondary, or driven clutch, is torque or load sensitive and controls how fast the shifting occurs. When the engine is at idle, the clutches are in a neutral position. As engine RPM increases, the drive clutch will engage the belt and start moving the track or wheels. This is referred to as engagement. As engine RPM continues to increase, the drive clutch forces the belt outward to a higher ratio. The driven clutch also shifts and maintains belt tension. If a vehicle load increases, the driven clutch will override the drive clutch and shift back to a lower ratio, which in turn keeps the engine RPM constant. The drive clutch is composed of two main components: the fixed sheave, which is attached directly to the engine crankshaft, and the movable sheave, containing the RPM controlling components such as the flyweights and the return spring. This clutch assembly works on a principle called centrifugal force. This simply means an object, such as a weight on the end of a string, creates an outward force as it spins in a circle. The amount of force depends on how fast the object is spinning and the mass of the object. To understand the drive clutch, you need to understand the forces going on inside it. To illustrate, let's say the drive clutch spring is sitting on the weight and the mounting pin through the center of the clutch is the center of gravity. As the clutch spins, the mass of the flyweight above the center of the gravity creates an outward force. Both the clutch spring and the mass below the center of gravity create an opposing force designed to keep the clutch assembly in neutral. When the force created by the weight spinning above the center of gravity overcomes these opposing forces, the flyweight starts to swing out. The roller starts to climb the flyweight and the clutch sheaves close together, shifting to a higher ratio. For different applications, the neutral flyweight position can be moved up or down to lower or raise engagement RPM. This is often referred to as a cut heel or tip down weight. The driven clutch needs to work in constant opposition to the drive clutch. The driven clutch assembly consists of four major components: the helix, the spring, the movable sheave, and the fixed sheave. The driven clutch components also control how fast the shifting occurs. To understand how this works, let's consider two hills. Hill A is fairly steep, and Hill B has a gradual slope. If we place a ball at the top of each hill and let them go down at the same time, which ball will hit the bottom first? That's right, the ball on Hill A. Now with the balls at the bottom of the hills, let's put someone trying to push each ball back up the hill. The ball rolls more easily up Hill B. This might seem like a silly illustration, but it accurately shows how the driven clutch works. The hill represents the helix ramp angle, and the person pushing the ball up the hill is the driven spring. This cutaway of a driven clutch shows the driven buttons, or the ball in our example, is sitting at the top of the helix. When speed increases, the buttons upshift or slide down the helix. When load increases or RPM decreases, the spring backshifts the movable sheave up the helix toward neutral. Generally speaking, a steep hill or helix is used for a quick upshift from a low to high ratio. It's like rapidly shifting your 5-speed car from first to fifth. A less steep helix angle slows down how fast the upshift occurs, but allows quicker backshift when encountering heavy load situations. The upshift speed must match the engine's power curve and the vehicle's load, or the engine will bog or over-rev. Upshift and backshift are controlled by the helix and driven spring working together. A straight helix may be good for upshift, but have poor backshift, or vice versa. Some driven clutch multi-angle helixes have a steep upshift for quicker acceleration from standing to a higher speed, and a gradual ending slope for a good high-speed backshift. In more current designs, the angles have been smoothed to form a radius. Snowmobiles have many different radiused helixes to solve a variety of clutching conditions. The chain case or final drive gearing plays a major role in the upshift performance. Acceleration can sometimes be improved by lowering the final drive gear ratio and raising the helix angle to match the engine power and vehicle load. In a properly set up clutch, the maximum desired operating RPM will be reached immediately after engagement under full throttle conditions. This operating RPM should be maintained throughout varying load conditions. The drive belt is an important part of the PVT system. It must efficiently transfer the engine's power to the drivetrain. Inspect the belt and its adjustments whenever a machine comes into your shop for service. To remove the belt, shut the engine off and lock the brake. Grasp the belt just beyond the drive belt and pull back and up at the same time. Slide the belt off as the driven opens up. Most PVT problems can be traced to a misadjusted or worn belt. Inspect the belt for abrasions, cracks, missing cogs, loose cords, excessive wear, or hourglassing. Refer to your service manual for more on belt inspection. What do we mean when we talk about hourglassing? Hourglassing occurs when the drive clutch engages a belt, but the belt does not turn. If, for instance, the track was frozen to the ground, or the parking brake was left on, or the customer tried to pull an oversized load, and RPM is continued to increase without the belt spinning, severe stress and damage will occur to the drive belt. This can be noted by smoke from the clutch compartment or the smell of burnt rubber. Stressing the belt in this way causes a wear pattern in the shape of an hourglass and is not warrantable. Hourglassing may also be evident by a thump or a vibration coming from the PVT system. A few basic adjustments are very important for top performance and long belt life. Belt deflection, belt to sheave clearance, offset, alignment, and component wear should be checked regularly in order to keep the clutches running at peak efficiency. It's important to note the lubrication of drive and driven clutch components used to be regular maintenance. Bushings used in Polaris clutches today are entirely self-lubricating. Additional lubrication will only reduce service life. Belt deflection is measured with a straight edge placed across both clutches. Push the center of the belt down to remove slack and measure the distance from the belt to the bottom of the straight edge. This measurement should be 1 1/8 to 1 1/4 inches. Don't apply too much force when checking deflection, or the belt may be forced into the driven sheaves and your measurement will be inaccurate. A narrow worn belt can cause excessive belt deflection by riding low in the driven and high in the drive clutch. Too much deflection can cause bogging, belt burning, or poor takeoff performance. It's like trying to take off in second gear with a standard transmission. Belt deflection is adjusted by varying the width of the driven sheaves. Some clutches are equipped with an adjuster plate. The adjuster plate has raised areas to allow up and down movement. For these, adjuster pins. The pins in turn force the movable sheave to close or open depending on adjustment. Number 1 being the tightest, and 5 being the loosest or most belt deflection. To adjust clutches without the external adjuster, it will be necessary to add or remove the washers from between the two driven sheaves. Remove washers to tighten belt deflection, and add washers to increase belt deflection. At least one washer must remain between the sheaves at all times on all driven clutches. The center distance between the clutches drastically affects belt deflection. If the previously mentioned adjustments aren't enough, it will be necessary to check center distance. All ATVs have a 10-inch center distance. All snowmobiles except Storms have a 12-inch center distance. Storms are 12.5 inches. Improper clutch alignment will reduce efficiency and decrease belt life. The two adjustments to check are offset and alignment. Offset is a distance measured between the back of the drive clutch and clutch. Proper offset allows the drive belt to run straight throughout the shift range. Alignment is correct when both clutches are running parallel to each other with the engine under load. When at rest, clutches may be slightly misaligned to compensate for the flex of rubber engine mounts. When power is applied, or when the vehicle is under heavy load, the engine will twist rearward slightly and the clutches will be parallel. Both offset and alignment can be checked at the same time with the appropriate tool. Place the clutch alignment tool over the drive clutch and slide the arm past the driven. On P85 systems, push the driven clutch completely inward toward the airbox. Offset is correct when the rear of the tool contacts the driven sheave, and the front of the driven has a 16th to 1/8 inch gap. Offset is adjusted by adding or removing shim washers from behind the driven clutch. On some systems, the driven must float freely on the shaft. After adjusting offset, add or remove shim washers from the retaining bolt to provide a 16th to 1/8 inch of float on the jack shaft. This will allow the driven to find its center line and also prevent side loads on the jack shaft bearing. If alignment is off, loosen the engine mounts and shift the engine as required to obtain the proper offset and alignment. Engine torque stops are included on some models to support the engine under heavy loads. Be sure to verify proper stop adjustment. On ATVs, a transmission torque stop is also used and should be periodically adjusted as described in the repair manual. Belt to sheave clearance is a distance between the drive clutch sheave and the belt with the engine off. Belt to sheave clearance is measured by forcing a new belt to one sheave, while measuring the distance between the other sheave and the belt. Optimum belt to sheave clearance is 10 to 30 thousandths. Excessive clearance can cause jerky belt engagement and may reduce belt life. If there is no clearance, the machine will creep at idle, be hard to start, or bog at takeoff. To remove the clutch, loosen and remove the drive clutch retaining bolt together with any spacers on the O-rings. Insert the clutch puller and tap on the T-handle with a soft-faced hammer until the clutch breaks free. Mount the clutch securely in the holding fixture. Check the tower to button clearance. On some snowmobile clutches, the tower to button clearance should be 1 to 2 thousandths. Adjust clearance by adding or removing shims behind the trailing side buttons. ATV clutches use a damping device behind the spider button. Late model buttons have a rubber back bonded to the inner surface. Earlier ATVs use an O-ring on the drive side and either an O-ring or a flat rubber washer on the trailing edge button. Refer to the appropriate parts or service manual for the type, placement, and shimming of the damping device. Before you disassemble the drive clutch, mark the cover, spider, and both sheaves with a permanent marker or scribe. This is necessary to maintain clutch balance when the clutch is reassembled. Remove the cover bolts evenly and remove the cover. Measure the spring free length and compare to specifications in the service repair manual. Check for distortion in the coils. The edges must be square with the base of the spring. To check the rollers, place a flat metal rod on the roller and pull. Each roller must spin freely without binding or feeling flat spots. Inspect the clutch bushings for wear. The Teflon or dark coating on this bushing is more than 50% worn away and the bushing must be replaced. Loosen and remove the lock nut and pull out the pin and shift weight. Note the direction of the weight pin with the nut on the trailing side. Inspect the surface of the weight. It should be smooth without dents or surface galling. Place the bolt inside the weight to check the fly weight bushing and the pin surface for wear. The weight bushing is not a service part, and both the weight and pin must be replaced if worn. P85 clutches have a jam nut on the spider. Use tool number 287-0338 to remove the nut, turning counterclockwise. All Polaris clutches have a standard right-hand thread on the spider. Turn the spider counterclockwise to remove using spider tool 287-0341. Notice that underneath the spider are shim washers. These shim washers set the belt to sheave clearance. Taking out shims will allow the sheaves to close farther, reducing belt to sheave clearance. Adding shims will increase the clearance. Shim part numbers are listed in the repair manual. Caution: if shims are not marked and the spider washers are lost or misplaced, the drive clutch may be out of balance when reassembled and must be replaced. In our case, the belt to sheave clearance was too wide, so we'll remove 1/20,000th shim. The spider buttons on P85 clutches are pressed in and can be removed using a special tool. Use an arbor press to drive the roller pins out of each leg. Discard the roller, pin, and thrust washer. Start the tapered end of a new pin in the spider, enough to hold one thrust washer in place. Be sure to check the end of the pin and remove any aluminum burrs before installing the new roller and washers. Use the installation tool to guide the pin during assembly. While holding the alignment tool in place, press the pin flush with the end of the spider. Check the roller to make sure it rotates freely and press the pin completely into place, flush with the pin bore. With the new buttons in place, install the spider, align the X's on the spider, and movable sheave. In order for the clutch to be in balance, the lines on the two clutch sheaves must be within 1 inch of each other after the spider is fully seated and torqued to 200 foot-pounds. Make sure the shims are in place in the spider recess as the spider is screwed into place. Notice that the spider screws down further due to the removal of the shim washer, and the sheave marks are no longer aligned. In order to make both marks align, we'll need to re-index the marked leg of the spider to a different tower. To do this, unscrew the spider and rotate the movable sheave to the next tower. This can be done because the sheaves have the greatest effect on the clutch balance. Now, when the spider is fully seated, the marks on the movable and the stationary sheaves are aligned. Torque the spider to 200 foot-pounds with the spider tool. On P85s equipped with a spider lock nut, install a lock nut and torque to 235 foot-pounds. Never use air tools to disassemble or assemble Polaris clutches. Install the spring. Align the marks in the cover with the sheave marks and tighten the cover bolts evenly to 90 inch-pounds. Before mounting the drive clutch, clean the crankshaft and clutch taper thoroughly. A tapered reamer can be used to repair the clutch taper if necessary. Ream the bore only if galling or damage is evident. Mount the reamer securely in a vise. Place the clutch on the reamer and turn in a clockwise direction. Do not apply excessive pressure or over-ream the clutch. To disassemble the driven clutch, turn the movable sheave clockwise 1/4 turn and hold with one hand. Using a soft-faced hammer, tap the helix down. Remove the snap ring and any backing washers, and then allow the sheaves to return. This should force out the helix. Before the helix is fully removed, note the location of the spring ends. Remove the helix and check the rams for smooth, even surfaces. P90 clutches have 2 spring locating holes in the helix and 3 in the movable sheave. This P85 driven clutch has 4 locating holes in the helix and 1 in the movable sheave. Both end tabs should line up. If not, the spring is fatigued and should be replaced. Inspect both sheave surfaces for wear or damage. Check the large movable bushing, as described earlier for the drive clutch bushings. If you can see more brass than Teflon, the bushing is worn and must be replaced. The small movable bushing is not Teflon coated on the P85s. Check for signs of abrasion or wear. Check helix buttons for excessive wear and replace if necessary. Be sure the clutch is clean and dry before assembly. Do not lubricate any clutch bushings. Install the movable sheave with belt deflection spacer washers. Notice the large backing washer used on P85s with the external adjustment feature. Remember that there must always be at least one washer in place between the sheaves. Install the spring in the movable sheave, selecting the proper hole on the P90s. Align the keyways or boss spline on the P90s and push the helix down about 1/2 inch. Select the proper spring locating hole and install the helix. While holding the stationary sheave, rotate the movable counterclockwise 1/4 turn and hold it in place. Press helix fully into place and hold. Install any backing washers and then the snap ring with the flat machine surface facing up. Locate the open end of the snap ring away from the keyway. And then verify proper operation of the driven clutch. As we talked about earlier, a properly calibrated PVT system will quickly bring an engine up to operating RPM and keep it there through varying conditions. System components such as the shift weights, springs, helix, and final drive gearing are factory selected for each model to match engine horsepower and approximate vehicle loads. You're probably already aware that clutching setups must be changed to compensate for any significant changes in altitude. An engine loses about 3.5% of its power for each 1,000 feet increase in elevation because the air is less dense. For example, an engine operating at 10,000 feet of elevation would produce approximately 65% of power than what it would have at sea level. Although the power cannot be regained, adjustments to the carburetor and drive system can be made to allow the engine to operate within its power band. With this in mind, let's look at a typical example. The customer wants a 1996 XLT set up for riding between 6,000 and 9,000 feet. Reviewing the specifications on the wall chart, we find that production clutching is a gold drive clutch spring with 10 M weights. The chart doesn't indicate a gearing change from 2139, but as a general rule, machines operated continually at high altitude benefit from lower gearing. The correct weight is a 10 MR with a blue drive clutch spring. The driven clutch remains the same. You can also refer to the hood decal, owner's manual, or the repair manual for clutching specs. Assuming the engine is in good state of tune and the customer is driving from a light load to a heavy load condition, there's a noticeable reduction in RPM. This is typical of a poor backshift or the PVT not shifting to a lower ratio fast enough. Poor backshift can mean too loose of a driven spring or too high of a ramp angle on our helix. First, try changing the spring setting. When disassembling, note the spring hole location on the helix. Move the spring up to the next higher hole for better backshift. In the past few minutes, we've covered a lot of information. Let's review some of the important points. The drive clutch is like a governor and controls the engine's RPM. Both upshift and backshift are controlled by the driven clutch. The clutches are designed to be lube-free and should not be lubricated. Earlier, we talked about the basic adjustments and how important they are to proper system function. This is because many of these adjustments affect starting ratio. At engagement, the vehicle must accelerate to an initial speed. Factors affecting this speed are engagement RPM, the ratio of the drive and driven clutch, transmission or chain case reduction ratio, and final drive ratio. A loose belt rides higher at engagement, creating a higher starting ratio. It is important to remember that the belt will slip until the minimum vehicle speed is reached. When belt slippage is excessive, extreme heat is produced in the PVT system. Continued throttle application when the vehicle is stationary is a common cause of belt burn. The belt may have thin spots in width or hourglassing, as described earlier. This will cause surging, erratic operation, or even a noticeable driveline vibration. Proper belt deflection keeps the starting ratio low. If the belt is too loose, it's like starting out in second gear on a manually shifted transmission. Belt to sheave clearance must be correct for smooth takeoff and long belt life. Improper offset and alignment will reduce belt life and clutch efficiency. Clutch balance is not affected when the clutch is disassembled for normal maintenance or repair. Re-indexing the spider is not required unless you add or remove spider shims to change belt to sheave clearance. Bushing replacement procedures for both drive and driven clutch are outlined in the repair manual. On ATVs, the clutches are sealed in a cover with an inlet and an outlet for air circulation. Make sure both ducts are clear so cooling air can circulate freely. The connections must seal properly to prevent water from entering the system. Polaris Variable Transmissions are designed to provide a long and trouble-free service life. Altitude, temperature, vehicle load, and riding conditions all affect PVT function. Applying the things you've learned in this video will help you, the Polaris service technician, consistently provide your customers with the quality and performance they've come to expect from Polaris.